We're going to walk through a example problem based on the American Gear Manufacturers Association AGMA gear design. We have all these details for this problem and the interaction of the two gears. For example, the pinion has 34 teeth. It applies 200 newton meters of torque at 3,000 RPMs. We need all those details. We got some information about the material. It's carburized and hardened, grade 3 steel. So it's got a surface hardening that's been done to it. The gear, on the other hand, is it has 50 teeth and it's through hardened from grade 2 steel with a hardness Rockwell B of 325. Both the gears have a module, of course, of 2.5. They have to have that to interface with one another. They have a 20-degree pressure angle. The quality on both is high, so it's leveled, graded as a 9. The teeth are crowned and lapped, so these are good conditions. They're precision and closed and centered between the bearings. There's no rim, so it's continuous. The width is the same all through the gear, so the rim factor is 1. We're targeting a safety factor of 1.1 for both the bending and the contact stress. We have a surface condition factor of 1. It's expected to operate and lubricate. It's lubricated and cooled to roughly room temperature with 99.9% reliability for 10 million load cycles. And the engine provides light shock power and the ride causes moderate shock. What are we supposed to do with all these details? We're supposed to calculate the minimum face width given the following constraints. What's our approach going to be? We're going to calculate not just one, we're going to calculate 2 face widths, one based on the bending criteria and one based on the contact criteria. But before we get there, we have to calculate the load and the modified load. So the load, we were told that the pinion has a module, so the gears have a module of 2.5 millimeters, and module equals millimeters of diameter per tooth. If you take the number of teeth, which we were told is 34 for the pinion, times 2.5, you get the diameter. So that diameter is 85 millimeters. So then to calculate the load, we take the torque, which is 200 newton meters, times the reciprocal of the radius, which is 2 over the pitch diameter, so that's 2 over 85. So 200 times 2 over 85 is 4.7 kilonewtons of tangential load, or 4,700 newtons. Now we have to modify that with our 4 factors. 4 factors are the overload, dynamic, size, and load distribution factor. Firstly, we were told that there is light shock in the power source and there's moderate shock on the driven machine. We put those two together and find the intersection in the matrix, and we get a KO overload factor of 1 point. Secondly, the dynamic factor. We need to calculate the pitch line velocity to be able to determine the dynamic factor. So the pitch has a module the pinion has a module of 2.5 millimeters, and we've already seen that since module is diameter per tooth, then we have a diameter of 85 millimeters. So a pinion running at 3,000 RPM, convert that to seconds. 3,000 RPM is 50 revolutions per second. Multiply that by the diameter, you get the surface velocity in millimeters per second, and then convert that to meters, and you get 13.3 meters per second surface velocity. So knowing the surface velocity, that gives you the horizontal axis. You can see the secondary axis that I added there, 13.3. So you find it's a little bit above 10.2, but not quite half the way to 20.3. So take that up to the quality grade, which was 9. We were told the quality grade in the problem is 9, and that gives you a dynamic factor of about 1.3. The size factor, again, it's worse for wider gear teeth, and it depends on the face width, and that's what we're asked in the problem to determine. So we don't know the face width. So if you don't know the face width, you need to make an initial guess. So you start with assuming, okay, it's going to be about 0.4 times the diametral pitch. So 0.4 times 85, that's 34 millimeters. 1 plus 0.4 times dp over 10 times dp is 1.04 because the dp's cancel. So we gotta first cut at a size factor, and then finally the load distribution factor. We have crowned teeth, we were told, so that gives us directly that first number, 0.8 for crowned teeth, and then you have to calculate based on the face width being less. We know it's going to be less than 430 millimeters. That would be pretty enormous. So we take our guess of 34 millimeters and our module of 2.5, and we plug that in. We can calculate an estimated C sub PF value. And we have 3 more constants to calculate in there, C sub PM. We said in the problem that the center line of the gear face is centered between the bearings. So we're going to take a 1 for C sub PM. And then the gear we were told was lapped, which is a very fine surface finish. So we have very fine gears, so we're going to take a bonus for that by taking a low C sub E, 0.8. Then C sub MA is an equation. We were told that this is a precision gear, and it's enclosed. Now, one thing about plugging in this equation, the A, B, and C coefficients were built for inches, not for millimeters. So if you convert the face width, our guess of 34 millimeters, to inches. So you see that's been done there. 35 divided by 25.4 gives us 1.34 inches. Plug that in, we get 0.0845. Put all 5 of those together, and we get a K sub M of 1.3. So we put all 4 of the coefficients to modify the load together, and we get 12.39 kilonewtons. So of the two things we're going to use, the two approaches we're going to use to calculate face width, first we're going to start with bending stress and the fatigue criteria and bending. Then we'll move on to Hertzian contact stress. So we've got our modified load, and we've got our module, and then we got to build the rest of these values. Got to build these into our equation. And we'll take these one by one. The first one is the rim thickness factor. We don't have a rim on ours, so we don't have to worry about that. We'll take 1 as the value there. And we have the modified Lewis factor, which also incorporates stress concentration, and that's Y sub J, also known as J in other equations. So we have 34 teeth on our pinion and 50 teeth on our mating gear. So you see here, went from 34 up to 50, then went over to the left, the y-axis, and that's about 0.395 for our geometry factor. Then we move on to the material aspects. So we picked a material. This gear has to be carburized and hardened, so it's very strong on the outer surface. So it has been surface treated, surface hardened to give us the optimal life. And we were told that we are looking at 10 to the 7th cycles. Now at the 3000 RPM that we were looking at, that is about 55 hours of operation for 10 million cycles. So the stress cycle factor Y sub N is going to be about 1. Now we know everything. We can plug those in. We have to make sure the units are going to work out though. So you see number 4 down here, we took the 75 KSI, multiplied it by the conversion factor, 6.89 megapascals per KSI to get 517 megapascals. Another thing we did is we had to convert the 12.4 kilonewtons to newtons so that it would cancel with the newtons in the denominator of the equation. Plugging all that in, there's a couple things I didn't mention. You got the temperature factor. We said we assumed a temperature factor of 1 for room temperature. Reliability factor, we just plugged in our 99.9% reliability, so that's 0.999 to get the reliability factor of 1.25. And we did mention that the safety factor that we're looking for is 1.1. So plug all that in, do the math, and we get 33.4 millimeters as the minimum face width. So that's how wide, or if we think of the whole gear as a unit, how thick that whole gear is going to be. So 33.4 millimeters. We're not done yet because we need to do the same analysis with the other failure mode, which would be contact stress. And let's see if it's worse or better. So the contact stress and pitting criterion solved for face width is shown here. Again, we know things about our gear like the pinion working diameter. That's just the diameter of the pinion. And we know the W sub T modified. I believe in the previous slide that was 12.4 kilonewtons. So we can fill that in, but we have these other variables that we need to go get or calculate. So first off, identify the elastic coefficient. We said we have steel on steel gears. So what does that give us? That gives us an elastic coefficient of 191 square root MPa. Next was our geometry factor for pitting resistance. This is an external gear, so we plug in the 20-degree pressure angle there. M sub N value is 1 for spur gears. M sub G is the speed ratio, so that's 50 over 34, that's 1.47. On the bottom here is 1.47 plus 1, so it's 2.47. That gives us a value of 0.111. And then we chose a pinion that was carburized and hardened, which gives us a very different contact strength number from AGMA. So watch out. the S sub C is, the S for contact is very different from the S for bending. It was 75,000 for bending. Here's 275,000. And then we were told that we need to look at 10 million cycles, which again gives us a stress cycle factor C sub n of 1. And since our pinion is surface hardened, we can get some credit because it's a benefit if the pinion is harder than the gear. And we were told that the surface finish on the gear is a very fine 16 micro-inch surface finish. So we go from our gear hardness, that's the Brunel hardness of the gear, 325, which we were given in the problem, up to the 16 micro-inch, and we go to the left, and we get that it has a hardness ratio factor of 1.08. So we plug in each of those numbers in the equation, and this is a weirder equation because it has some squared stuff. So it can go pretty wild pretty fast. But we still have to make sure that the units cancel. So we have 12,400 newtons. We have 191 square root MPa. So I took that out of the square root. I squared the square root MPa. So this is basically MPa right here. Megapascals is newtons per millimeter squared. Here's another megapascals, newtons per millimeter squared, but it's squared. So this gets rid of one of those, and there's another one left over. So there's going to be millimeters is all that's going to be left over. And so that's what we end up with over here. That's how that equation works in terms of units. The rest of these things are unitless. They're unitless factors. We covered everything in here. Again, the temperature factor is 1. The reliability factor is the same as the bending stress, so it's 1.25. We convert the contact stress to megapascals to plug it in here, so that's 275 times 6.89, and so we get 21.6 millimeters. Now, in our previous approach, determining the face width from bending stress, we got 33.4, and that is the minimum face width I can have for bending stress. So that has to be my face width, because if I take the minimum for contact stress, I'm going to be below the minimum for bending stress, and it's going to fail. My gear is going to fail due to bending. So the conclusion is that my face width needs to be at least 33.4